Welcome everyone. In today's lecture, we'll be looking at probabilistic motion models. What this essentially deals with is to understand the uncertainty that's involved while a robot is moving. So the uncertainty in the motion can come due to multiple reasons. This could be because, let's say, the wheels of the robot slip on the floor, or this could be due to the fact that we give a certain command to the robot, but the robot doesn't reach this velocity instantaneously. So the motion that the robot executes is not the one that we actually expect it to do. And this is one of the reasons, or one of the many reasons, that introduces uncertainty in the motion for a robot. So in the previous lecture, if you remember, what we saw was basically how different types of robots, so mainly different wheeled robots, move based on the control input that we give to them. So we saw how differential drive robots work, we saw how Ackermann robots work, but there we always assume that the control will be followed by the robot perfectly. In today's lecture, what's changing is that this motion is a bit uncertain, and we want to understand how to model this uncertainty, and generally we'll be using simple probabilistic models to capture this uncertainty in the motion. Then what we'll also look at is how these motion models, the so-called motion models, can then be used for state estimation problems. Since now we can both model the movement and the uncertainty in the movement, we'll see how this fits into our Bayesian framework for state estimation. Okay, so let's get started. The main theme in this lecture is basically the fact that the motion is inherently uncertain. And this uncertainty comes from multiple reasons. So for example, if I ask the robot to move 1 meter forward, in practice, maybe it just moves 95 centimeter or 1.1 meter and 5 centimeter and so on. So this could happen, for example, typically, for example, in a differential robot, we set the velocity for the left and the right wheels, and this moves, or this drives the robot. However, suppose we ask the motors to rotate at a particular speed, it may not actually achieve this speed instantaneously. This results in the fact that the distance that it travels is less or more than we actually expect it to be. And the question that we will look at today is how to then model this uncertainty out there. So just to have an example here, what we see here is a maze environment, and the robot starts here and then goes around this maze all around basically. And the red line here actually shows the path that's actually traversed by that robot. However, the robot thinks that it actually traversed this other red line that you see here. And what's happening here is that the internal estimate, or the odometry of the robot, is drifting. So there seems to be a tendency to always estimate that it goes a bit right than it's actually going. This may be because of an imbalance in the way the weight is distributed on the robot. Maybe one of the wheels has more tire pressure than the other one. What we end up is kind of a systematic drift over time, and this is, so to say, the uncertainty that's involved while executing motion. So the question that we ask here is, given the actual movement here and the odometry, or the estimate of the model here, how are these two linked? So how can we actually map this uncertainty between them? And if you think of it in terms of probability, what we are exactly calculating is the probability of a robot ending up at xt given, so this line here is read as given that you start at xt minus 1 and execute a particular command ut. And this probability distribution is also called as motion model, because essentially it models, if you start at xt minus 1, what's the probability that you end up at xt. And if you again think of this example where I asked the robot to move 1 meter, this probability would, for example, be meaningful to ask, say, around 1 meter, say at 1.1 meter, what's the probability that I end up at, say, xt equals to 1.1, given, for example, we start at the origin. And so this probability we can compute for different positions in the world. So we can compute it at 1, we can compute it at 1.1, we can compute it at 0.99, and so on. So what we expect is that if we ask the robot to move 1 meter, the highest probability should be around 1 meter mark. And what we basically encode using the whole probability is what's the distribution, or what's the probability at different points or different locations in the environment for the robot to land up in. And the way this relates to our state estimation framework is in the following way. So if you recall from the lecture from recursive based filter, we had come up with a recursive formulation for estimating the belief. So this is the probability that the robot is at xt. And we had come up with a formulation that depends, or is recursive, so that depends on the belief at xt minus 1 and is then modified by a certain parameter here. So there are two parameters here. One, the one which is the focus of this lecture, is to understand how you move basically from xt minus 1 to xt. So essentially what this equation is saying is that go over all your previous positions, so xt minus 1s, then multiply them with your motion model probabilities of ending up in a particular place, sum them up, and then we will see what this particular term means later on. So this is the place where we need this knowledge of how the robot moves, or how the probability distribution is when a particular action is made. And if you remember again that we had these two main steps, a prediction step and a correction step in the base filter estimate. And what we just saw is what is also called as the prediction step, because we are looking at all the positions, so all the positions xt minus 1, and we're looking at the probability at xt minus 1 and then propagating it through the model, so through the way we propagate this motion given, or the control that's given by ut to give the predicted belief here denoted by the bar on top. And then what would be the main focus of the lecture on observation model would then be how does the measurements taken by your sensor then modify this belief. So typically what happens is that you make a movement. This movement usually introduces some uncertainty. And then you take a particular measurement zt. This could be, for example, a GPS measurement. This could be from a laser scanner. This could be from different sources. And often it works in the way that the motion model or the motion step introduces more uncertainty, whereas the measurement step decreases this. So this is the way in which these two models help us estimate the state of, for example, where the robot is in the environment. Right? So to be a bit more formal, when we talk about motion model, and in particular here the probabilistic motion model, what we want to compute is the posterior probability. It's posterior because we want to find out what's the probability of xt given certain conditions. And this condition is that given that you're at xt minus 1 and you apply a certain command ut, what's the probability that you will end up at xt? So if you think of the different drives that we saw in the previous lecture, or in the lecture on locomotion, this ut could be, in a differential drive case, the velocities given to the left wheel and the right wheel. If you think of an Ackermann drive, this could be the linear velocity, the angular velocity, as well as the steering that you set for your robot. And it holds not just for wheeled robots, but also for robots in general. This could be, for example, a quadricopter where you give different commands to the propellers that you have, a humanoid, or whatever. The main idea is when you give a particular command, what's the probability distribution of ending up at different places in the environment. So what we'll focus in today's lecture is mainly on wheeled robots, and we will see two commonly used models which kind of abstract different motions for wheeled platforms. And these two typical models are what are called as the odometry based models and velocity based model, also sometimes called as the dead reckoning approach. The difference being the following. So in the odometry based model, we set a particular command to our robot, then it executes this motion. What we do then is to attach some kind of a sensor to the motor shaft to understand how this motor is rotating. Then we use this information to figure out how much our platform has moved. So in a way, it's a feedback system where we put the control and then see actually how the platform has moved. So technically speaking, you could treat this as a measurement, but the way we will treat this in this course is to treat odometry as basically a control command, because it's a measurement of how basically we moved. And the second model, which is also quite commonly used, is what is called as the velocity based model. In a sense, this is just a look ahead step, in the sense you don't actually measure anything. You say to the robot, okay, go with this velocity and say linear velocity of 1 meter per second and an angular velocity of 3 degrees per second. And then you just use your physics of your platform to figure out where you end up with. So we can see this a bit more in detail. So this is related to the odometry model. And what you see here is kind of the setup that you have for wheel encoders. So what happens is you usually use this kind of disk which has alternating white and black lines, and you attach this to the shaft of a motor. And therefore, when the motor rotates, this particular disk also rotates. And then there is some associated electronics which figure out when you move from a white line to a black line. Often it results in a peak, and therefore what we can do is to figure out exactly how much the motor has rotated. And then understanding how much the motor has rotated, we can then translate this into how much the platform itself has moved, as let's say, for example, the wheels are directly attached to the motors and so on. So when we talk about odometry models, usually the robots are equipped with some kind of encoders which give us, so to say, an internal state of how the motors are moving. On the other hand, when we talk about the velocity based model, or what is called as dead reckoning, what we do there is in a way a prediction. So we know how our platform moves when a certain control command is given, and we just use the equations that we develop, for example, for the differential drive of Ackermann drive, and then we figure out where the robot would end. In practice, the odometry model often gives a better or higher accuracy measurements than the dead reckoning, because in a way the odometry model captures the rotations after the command has been executed, where in the dead reckoning model you just wish that, or you hope that this particular command is executed, but you actually don't know what happened in between. So in practice, we often use the odometry model to do the motion. And now what we'll look at is why, or from where does this uncertainty in the motion come from, and in particular we will see this for wheel robots. So the ideal case is, for example, here where we have the two wheels of exactly the same diameter and it's flat, and if it rolls smoothly on the floor, we would expect that it makes the movement that is, say, defined by the differential drive robot, by the differential drive equations or by the Ackermann equations. But in practice, what can happen is that as it moves in the environment, say it goes over a piece of wire or a stone or whatever, and then this causes there to be a bump. And what often happens is that you, or for example in this case, this right wheel here would skip certain revolutions, and with this you would end up thinking that you covered a different amount of distance than you actually did. What can also happen is, for example, you may have different wheel diameters. This could be because of, let's say we pumped the two wheels differently. This would be a stupid thing to do, but this is one way this could happen. The other way would be, for example, usually the robots would carry some kind of a load, and then if the load is not evenly distributed, it might happen that there's more pressure on one side than the other. Whereas when we use equations of motion, we might not know this, and what we end up in terms of an estimate of where we go is different from the actual motion that the robot performs. Also, it could happen that we are moving on platforms, maybe in this case a carpet or a slippery floor, and the wheels may not be perfectly rolling on this surface. And in this case, again, what happens is that we are not able to perfectly figure out how much the wheel has rotated, and therefore we make a mistake in seeing how far the robot has actually moved. So what we'll do in this lecture is that we'll abstract a bit away from the exact drive. So we will not talk specifically about differential robot or Ackermann, but we'll see two models which kind of sit on top of this, which kind of generalize this, and it also makes our analysis for deriving the equations a bit easier. And the first of this model, like we said before, is what is called as the odometry model. So in this model, what happens is, suppose at time t minus 1, we start at this positions x bar, y bar and theta bar, and at time t minus 1, we end up at the x prime, y prime and theta prime positions. And the way we would now express the odometry command, so to say, is by these three motions. We say that the motion between any 2 points can be explained as a delta rotation 1. So you rotate first, then you translate by delta translation, and then you do a rotation by delta rotation 2. So this is just an abstraction over the actual movement. So for example, if you had a differential drive robot, maybe the robot actually moves along an arc, but for the sake of analysis, what we say is that our control commands in this case are broken down into this model, where each motion is basically a rotation, a translation and a rotation. And some equations here to figure out what these rotation values are. So we know that we start at this position and we end up at this position. So it's the position and the orientation, so the pose. And so for example, to figure out what's the translation that we moved, it's essentially the distance between these two coordinates, and this is what we see here. Whereas the angle, so the delta rotation 1, again can be obtained by taking the tan inverse of the difference in the y's and the x coordinates, subtracted by the original orientation that you have. And similarly, the delta rotation 2 is what's left after removing the delta rotation 1 and the original yaw angle that you had. So these are just equations for our odometry information. So from now on, in the odometry model, we'll assume that the odometry commands are basically defined by these three parameters. So 2 rotations and a translation. So now that we understand what the pose is. So the poses in this case are a 2D, the robot lives in a 2D world. So it has an x, y position and a yaw. And the control commands are these three things here. So the next thing to understand the uncertainty, so to say, is to model how the noise is there on these different parameters. So one way would be, for example, if you start here, you could say that we roughly end up here, but with, let's say, a Gaussian distribution around this place. This could be one assumption. So we start from here. Very likely we end up here, but we might also end up a bit here, and this noise could be Gaussian. But often in practice, what's seen to work better is, rather than assuming one big motion which has Gaussian noise, we model the Gaussian noise on each of these different commands. So we have a delta rotation 1, a delta translation and a delta rotation 2. And how we model is that there's a Gaussian noise, and we'll see that in principle, this need not be just Gaussian. So it could be any model which explains your noise well in reality. And basically, we would have 3 separate Gaussian noises, let's say, on the delta rotation 1, the delta translation 2, and the delta rotation 2. And we should note here that the resulting noise that would end up in the final position would not be a Gaussian as before, because the equations like we saw before, these equations, because these determine how the motion actually happens, are nonlinear, and therefore when this Gaussian noise propagates through these nonlinear functions, we would end up with some function here which need not be Gaussian. And the reason we do this is, in practice, we observe that this particular model explains the actual noise often better in real world. So let's go a little bit more into details of how actually we model this Gaussian noise. So like we said, so for each of the parameters, so the delta rotation 1, the delta translation 2 and the delta rotation 2, we model noise terms. So this epsilon here models the noise on those parameters. So these are the mean movements. So let's say, for example, this is the rotation that we ask the robot to do, and then there sits a particular noise on top of it. And this noise, we model it depending on 2 terms. One, This noise depends on how much you ask it to rotate. So this alpha 1 is kind of a coefficient which says what's the, so if you ask the robot to rotate 30 degrees, what's the error? While if you ask it to rotate 60 degrees, what's the error? So intuitively we know that the larger the motion we ask it, usually the higher the error is. And in the general or in the typical model, there's also a certain amount of, or there's a certain effect of the translation that you make. So if you make a larger translation, it's possible that you end up with a rotation error which is also larger. Similarly, in the delta translation, we model the noise in terms of the length that we cover, and it's also a function of the two rotations that we have. So we have terms. So here basically we have 4 terms. So alpha 1, which let's say maps the error in the rotation part, alpha 2, which maps the error in the translation parts for this case, and then we have an alpha 3 and alpha 4, which, so to say, capture the effects of translation on translation and rotation on translation and so on. And again here alpha 1 and alpha 2 are the same as in the first case. So this random variable in general, we would assume it in most cases to be normal distributed because it's the distribution we use most often and also what is observed in reality. But nothing stops us from defining this as any other distribution that might be meaningful. And for example, one such distribution is the triangular distribution. So it looks very much like a normal distribution, apart from the fact that in the normal distribution, even if you go very far away, even if you're at infinite, for example, there is a very small probability, but still a probability of you being, let's say, infinitely away, which in the case of robot's movement is equivalent to the robot being kidnapped, for example. If you know that this is something that won't happen in your system, you could model your noise using a triangular distribution where you ensure that your uncertainty is within a bound and you never go out of these bounds. Right? And what you see here are basically the equations for how, or basically this is the equation for the normal density function, and this is similarly an equation for the triangular distribution. So given all this information, we want to come back to our main question, which is to figure out a way to compute this probability distribution. So again, we sit at xt minus 1, we make a control command or an odometry command, in this case ut. So if you consider the odometry model, this would be a rotation, translation and a rotation. And we want to compute the probability of ending up at different positions. So this is the probability that we want to compute overall. And just a point to note, how do we actually calculate this probability at a particular point? So it's just again the equations of a normal distribution and a triangular distribution. But what we see here in terms of A and B are what are here called as query points and standard deviation. So the query point in our case would be, suppose we expect the robot to end up at, say, x prime. The query point would be, say, for any given x. So x minus x prime would be, so to say, how far you are away from your mean expectation. And for that particular query point, this would be the probability distribution that's given by the normal equations. And similarly, if you use a triangular distribution, this would be that particular probability distribution. So for example, now we ask the robot to move 30 degrees. Right? So the mean movement that we expect is 30 degrees. And suppose I ask, what's the probability that it actually moved 45 degrees? Then the A would be 45 degrees minus 30 degrees, whereas the B is, so to say, the standard deviation which we need to understand from the motion of the robot itself. So usually what's the error that we expect in this particular movement that's there. So now that we have this, we come out with an algorithm which actually summarizes the procedure of computing these probabilities. And so the result of this algorithm is this probability distribution that we want to compute. And in this case, we want to compute it between a hypothesis x and x prime. So our hypothesis is that we start at time t minus 1 at x and we end up at x prime. And the x bar and the x bar prime are what we know from our odometry measurements. So first what we do is basically convert our odometry measurements into our odometry model commands, so to say. So what we have here is that if we had actually moved from x bar prime x bar to x bar prime, this would be the equations that we exactly saw. So these are the movements in terms of the translation in the two rotations. We compute exactly the same things for our hypothesis. So if we want to figure out what's the probability that we end up at x prime, given that we started at x, we again convert this into our model, which are the rotation, translation, and rotation. And then what we can then do is for each of these movements, so the rotation, translation, and rotation, we can compute the probability of these movements actually having happened. And we can compute it given the mean position or the difference to the mean position here, and the noise that we model on that particular motion. And then we assume here that these three motions are independent of each other, and therefore for this particular hypothesis, the probability distribution ends up being the multiplication of these three probabilities that you saw here. So what we did here is to have kind of an algorithm to figure out what's the probability of moving to x prime from x. And then we would need to repeat this for all the positions in the environment for which we want to, want to compute this probability or the motion model probability. And if we visualize the result, what we end up is something like here. So we start here at x, then we give a command u, and what you see here, it's a visualization of the probability distribution. So we see that this larger or the more black areas here correspond to the place where you are more likely to end up, and the places away from this from the center are lighter, representing the fact that you are less likely to end up there. And the fact that this is shaped in this what is often called as a banana shaped distribution is in this case because the robot might have a greater error in the rotation components than the translation one. That's why we see there's more variance along the angles with respect to along the translation vector. So in case if all the errors were say exactly the same, we would see a more circular distribution here. And of course this depends on the path that the robot itself takes, because it's something that's propagating over time. So for example, if we take this particular path here, we might end up with the shape which looks like something like here, right? So in this case, what we actually did is to go to each one of these places. So for example, we make a grid around the final position, and then for each one of these grids, we basically computed this this algorithm, and then we ended up with different values. So here, of course, it's plotted in 2D, but in practice, it's a 3D case where you have the x, the y, and the orientation. So this is one kind of representation, also sometimes called as the histogram representation, because we basically discretize our world and we have one probability for each one of this grid in the world. Another way to represent this is through what is called as a sample-based representation. Essentially, what we see is a general probability distribution function, and the sample representation would be the blue things that you see here. And the idea here is that the places where there is a higher density, we have a more number of samples being sampled from there. And in some of the Bayesian implementations that we'll see in this course, we'll see that it's better to have a sample-based representation than a histogram-like representation like we have before. So what we want to compute in terms of, let's say, the motion model is we want a sample-based representation for the motion model. And this requires us to first know how to sample different distributions. And the first distribution that we know how, or that we would like to distribute, that we would like to sample from, is a normal distribution. And there happens to be a very simple way to do this distribution. So if you have a standard deviation of b, the way to compute these samples would just to take 12 of such uniformly distributed numbers, add them up and divide by 2. Okay, so this gives a distribution which looks something like this. So here we take 1,000,000 samples, and as we can see that the distribution of these samples looks like a normal distribution. And we can do this for a triangular distribution as well. So it happens, we won't look into the proof, but basically it happens that if we compute a sample from this particular formula here, we can end up with a triangular distribution which looks like this. For example, if we have only 1,000 samples, there's still some error in terms of approximation, but the more samples we take, the more closer we get to an actual distribution. So here we have 1,000,000 samples and we are quite close to a distribution that looks like a triangular distribution. And when we have this sample-based model, we could think of them as a simulation. So suppose we have 100 samples where we start from. So these would be 100 different xt minus 1s. And then for each of this sample, we compute the motion for each of this sample and add the noise based on however we model the noise. And we end up with these new poses. So for each one of the poses, or each one of the robot position xt minus 1, we make the motion, we sample some noise around that motion, and this would give us a new probability distribution of where you will end up with. So what the motion model actually describes. And we can summarize this in an algorithm here. So what you have is your position at time t minus 1, which is x, and then the control command u. Again, in the odometry model, this would be a rotation, translation, and a rotation. And what we do is then the first motion can be thought of as a rotation that we actually want, and then we can sample from one of the noise distributions that we saw before. So this noise distributions, for example, in this case is exactly the one that we defined before, the one which depends on the amount of rotation that you give and also on the translations that you give. And we again repeat this for all the 3 motions. And then what we do is basically we propagate these motions using the motion model. So what we have here is that if we start at x, we end up at x prime, which is nothing but x plus the translations that we took times the cosine of the angle plus the rotation that it made, including the noise that we sampled. So we will end up in place that we expect plus some noise around it. And so what this will help us is to come up with a new x prime, y prime, and theta prime, which would be the place where the particle would end up with. And in this case here, this sampling could be from different distributions. It could be from a normal distribution, as it says here, or a triangular distribution, or some other fancy distribution if you come up with which describes your motion well. So how this looks in the end is what we see in the bottom here. So before we saw this histogram kind of distribution where we had the, let's say, the shade of black here, the shade of gray here representing how probable it is to reach here. What we see here is, say, these are the different samples which could be the places where you would end up with. So you can see roughly that the shape is similar to the histogram one, and in each of these cases basically it characterizes different noise parameters. So in this case there's more error on the angle, so it's more banana shaped, whereas in this case it seems that the robot has more error along the direction in which it moves, and therefore it's the error is larger, or the variance is larger along the motion, whereas again in this case it seems that the error again in the angles is much larger than the one in translations. Right. So let's see a simple example where what happens here is that the robot starts at this position and it executes this particular trajectory here. And when you start, typically it happens that you know exactly where you start from, and then you execute a motion. In this case, we show or we represent this using the sampling based approach, and we execute the first motion. We see that we have more uncertainty, which is captured by the spread of these particles or these samples, and then we execute another motion and so on. And after executing this whatever 10 commands, we end up with a probability distribution which is quite spread. So we could have done, or we have done here in this case using the samples idea, but we could have also done the same using the histogram idea, where we would query for each point in the environment or in the configuration space, what's the probability of ending up there. So we've in general seen two approaches. One where we look for each, so to say, grid in our environment and compute this probability distribution, so P of xt given xt minus 1 and ut. We've also seen a simulation kind of way where we add this noise while doing the movement. Right. So we'll also quickly look at the other model that we mentioned before, so the velocity based model. Here basically what happens is that the command is described by the linear and the angular velocity for that robot. So when you set a linear and an angular velocity, this robot moves along some circular arc. And yeah, so this is also one way to model how a robot can move. And in this case, the way we model the noise is on these parameters v and omega. So v being the linear velocity and omega being the angular velocity. So we could say that our linear velocity is affected by some amount of noise, here shown by this epsilon. Again, this epsilon depends on, let's say, the magnitude of the velocity of the linear and the angular velocity. And similarly, the error on the angular velocity again also depends on both these magnitudes, each one of them having their own coefficients. However, there's a small problem with this method in the sense that the state that we want to track is having 3 dimensions. So we want to track the x, the y, and the orientation. The controls here are only 2, so there's a missing dimension, so to say. And the way to think about this is that if we give a particular linear and an angular velocity, this corresponds to a particular arc that this robot traverses. But what we are missing is the orientation along that arc that it travels. So you could end up, say, at the same position on this arc, but having different orientations. And with this model, we lack the ability to model this error on this third orientation parameter. So what's often done in practice is to have an extra error term here shown by gamma, which we'll then see is added to the final orientation of the system. So here we won't go through the proof of how these equations come up, but basically these are the motion update equations when we use the velocity model. So the commands are basically v and omega. Here they're actually v hat and omega are the ones which have the noise already added to them. And so here what happens is that if you start at x and then you apply a particular command v and omega, you end up at this x prime. And this guy also, or these equations also include the noise as we model the noise in the v using this v hat here, which captures the noise in the linear velocity, where this parameter captures the noise in the angular velocity, and this gamma term which would capture then the error in the orientation. So with this we have a model for describing the noise for a velocity based model for wheeled robots mainly. And what the results would look like is what we see here. So visually they look very similar to what we saw from our odometry model, but for certain robots it's not possible, say the robots are not equipped with some encoders. In that case, we often use this velocity model, since all we have is the commands that we give them. And in practice, like I said before, usually these velocity models are less accurate than the odometry models, since this is, so to say, apply command and then just you don't know what happens, rather than having a feedback about how much the robots moved. So we saw basically 2 different kinds of models: an odometry model where we have these revolutions and therefore we can figure out how much the wheels moved, and this model where we just know the commands and how the robot moves. So with this, what we have is ways to describe the motion as well as to describe the uncertainty about that motion. And then when multiple of these commands are executed, these errors add up, resulting in the drift like we saw in the initial image. So just to summarize, what we saw are 2 kinds of models. So the odometry based models, where we have encoders on the motors, a velocity-based model where we just know the commands that we gave to the robot. And then we discussed a couple of ways to calculate this probabilistic motion model. So what we also call what we can also call as the posterior probability of ending up at x prime, given that you start at x and you apply a command of u. We saw a model where we can query for each point in the space to figure out what's the probability of ending up there. But we also saw another method where we can propagate a sample to figure out where we would end up in a simulated style of way. And both of these methods we'll see in further lectures how to use them for state estimation problems. And typically, just a note here is that all the calculations that we do is given a fixed time interval delta t. So we assume that these odometry commands hold true for that fixed time interval delta t. And in practice, if we do this fast enough, say 100 times a second, it's almost equivalent to having a continuous integration of these commands, right? So with this, I would also like to point you to the literature for this lecture. So if you would like to know more details or figure out the proof for, let's say, the velocity model, you could refer to the chapter 5 in Probabilistic Robotics book, and in general is a really nice book to understand the different concepts that we cover in this lecture. With this, I thank you for your attention and see you in the next lecture.